So we'll make one final homework this Thursday. It'll be due next week on Thursday. And then, let's see. I just also want to say that we're going to review from the 11th to the 13th. Two, three, four, five. You're doing 6. Last one will be 7. Okay. So before we talk about new notes, I want to do one more word problem. And I gotta find it. All right. We have a group of people who meet and shake hands with each other. And we're going to do 3 parts. First part, how many handshakes occur if there are 4 people? Okay, so we're going to draw a dot for every person and make sure all of those people have a connection with each other. Let's start here. So I have 4 vertices in this graph right here. This person shakes hands with that person and that person and that person. Let's go this way. Here, we've already shaken hands with the person next to us, and then let's go across and to the other side. Okay, this person has met with that person and that person. You still need to go here. And this should be fine with the connection, 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 back to the beginning. So what we want is the number of handshakes, which is going to be the edges. So how many edges do we have? We're going to just count, but also we're going to use the formula. Counting 1, 2, 3, 4, 5, 6. But there's a formula for finding the number of edges. Okay, so you get the sum of the degrees. This is degree 3, degree 3, degree 3, degree 3. One, two, three, four of those. And then divide by 2. So it's the sum of the edges divided by 2. Sorry, the sum of degrees. All right, one more try. I just want this to be clear. Number of edges is what we're looking for. Okay, and that's going to be the sum of degrees divided by 2. We'll just count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 degrees total. So that's adding up all of the degrees. And then divide by 2. Okay, cool. I got 6. Part B will have 5 people who meet each other. So 5 dots, 5 vertices. Let's put them kind of just in a circle, standing around. Okay, those are my people. Each person meets with all of the other people. So we're going to connect. Let's just start here and connect this person with all of the other people. Let's go here and do the same thing. So there, there, there. That's good. Connection, connection, connect, and connect. We got this one, that one, that one. Need one more. And then let's see, connected, connected. Good. We're back to the beginning. Okay, we're going to do this again. The number of edges is the sum of degrees over 2. And like every edge is a handshake. So we're finding the number of handshakes. Okay. This is degree 1, 2, 3, 4. Label every vertex with its degree. 1, 2, 3, 4. Another one of those. So the sum of the degrees is add all of those numbers together. So 4 plus 4 plus 4 plus 4 plus 4. 4 times 5 would be 20. 20 out of 2 gives us 10 edges, or 10 handshakes. You could also count in this picture. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Last one. For this example, we have 6 people who meet? How many handshakes? All right, let's draw every person kind of standing in a circle. And it's the same situation where this person connects with all of the other people, make sure this person has a connection with everybody, and do the same for the whole group. Across, 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 and connect. Let's go this way. We've done this connection, and then shake hands, shake hands. Okay. Let's see. 1, 2, 3, 4, 5. Each of these should have degree 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. Let's check. 1, 2, 3, 4, 5. Yes. So just going to put those degrees on the side for every vertex. Okay, that was previous answer. So we're looking for the number of handshakes. And in this picture, a edge is a handshake. So we're looking for a number of edges. So we find the sum of the degrees and then divide by 2. So 5, 10, 15, 20, 25, 30 total. So 15. Okay, so that's 15 handshakes. All right, so there will be, let's see, why is it divided by 2? Oh, it's first of all a theorem, but also it's kind of like for every, let's see, every edge, how do I explain? Let's just state the theorem. So from previous notes, at the bottom of this one, is the number of edges is half of the sum of degrees. I'll try to explain, but let's just at least write that down. Okay, so let's see. Used to lead to that theorem with a lot of pictures. So looking at the picture, every edge has to connect to a vertex. So it's always going to have, I guess, 2 degrees contributing to the sum of degrees. So the sum of degrees always needs to be even, and the number of edges will be half of that number. And we're never going to have a fraction of an edge. Edges are always whole numbers. Let's see if I've explained this well enough. Okay, I'm going to try to talk a little more about this with some pictures. Part of me is thinking we want to talk about something simple like just one edge. And then something like this to this, and like a loop. Okay, so this edge adds a degree here and a degree there. And the sum of degrees is 2. And the number of edges is the sum of degrees divided by 2. So that one edge, that one line right there. So like 2 vertices, 1 edge. Okay, this has 2 vertices, 2 edges. Degree 1, 2, 3. So the sum of degrees is 4, and then divide by 2, and that will give you how many edges. And I hope that helps. I think it did. Let's see. Oh, cool. Thanks. Yeah. Pictures help. Let's wrap this up with this number of edges. This one would be 4 over 2, which is 2. Okay, so we're going to start something kind of new. It's called a walk. We're going to talk about a walk and a path and a circuit. Okay, first one. A walk. It is a sequence of vertices, each connected to the next by an edge. So you can have, let's start with a graph. Have this graph with 3 vertices. A, B, C. Let's just draw a triangle. Connect A to B, B with C, and AC. And we're going to go A, B, C. A, and then the right arrow, this right arrow is just meaning like continue the notes, and then notes continue at vertex A goes to B, like this, right arrow B. B goes back to A. And let's go back to B. So we've gone A to B, to A to B. Let's go to C. Let's go back to B. So again, this block, it goes from A to B, back to A, then to B, then to C, and to B. So we can cross over an edge more than once if you want to with that definition. This is a block. Let's do one more. With the same graph, we're going to go C, A, B, C, A. C, A, B, C, C to A, to B, to C, to A. Okay. This one is also a walk. Let's get color. So let's do that journey again. We start at C and go to A. So right next to each other, we've got C and A. So is this good? A goes to B, and then go to C. And we're going to cross over this edge one more time, C back to A, which is okay because it's just a walk. One more with this picture, just getting messy. Okay, something like, we need a new graph. Let's do a square. Square with W, X, Y, Z. Okay, for this graph, let's start with doing a walk, and then we're going to do something that is not a walk. Let's do W, X, Y, X, W. W goes over this way, down to Y, back up to X, and across over again to W. So W over to X, X down to Y. Y goes back to X, and then X goes over again to W. That's a block. Okay, an easy one that's not a walk would be something like WY. They're not next to each other. Okay, we'll practice more in a bit. The next one is path. So a path is a walk, but you have more rules. Okay, so again, a path is a walk. It is a walk, and you do not use an edge more than once. So this means if you go over an edge, you can't go over the same edge again, like we did before. We'd go A to B, back to A, over to B. That was okay for walks. But with paths, if you go from A to B, you can only keep on moving somewhere else. You can't go back and repeat over the edge. Okay, let's see. I have that same triangle. The first example. A, B. Oh. Let's put A on this. Okay, ABC is a path. You go over this edge just one time, and the next, those vertices are next to each other. And you go over that edge only once, and so everything's cool without definition. Let's see. Let's just put CA. That's also a path. You cross that edge just one time, which is cool. And the definition for path. CB. Actually, I'm going to go this way. Okay, but if you do CACA, that is not a path, that's a walk. So going here, and then back here, and then even one more time. It's not a path. Okay, so we said CA is a path, but something like CACA is not a path, it's a walk. Let's talk about the last definition. So we want to talk about a circuit, which is a path that ends where it starts. So with that first definition, it was open. It's a sequence where each vertex is next to each other. Then a walk is more strict, and a path is even more strict. A walk is the sequence, a path is strict, and a circuit is more strict, like more rules to being a path. C-I-R-C-U-T. Let's draw that square.
Professor,
Yeah.
would it be like right to say that each, in the terms of like an ascending order, like walk to then path to then circuit, each includes an aspect of the previous one? Does that make sense?
Yeah, I think actually you should, let's do a quick summary. So there's walk, path, circuit. Okay, so you have walk, and then a path is a walk, and then a circuit is a path. And usually what I just put here is this is just some sequence for path. Don't reuse edges. It's a walk, and don't reuse edges. And then a circuit is a path. So you have this sequence with vertices next to each other. You haven't reused any edges, and the end is the same as the start. Let's put a dash. That way I can do this and okay. So yeah, circuit has to meet these rules, and that rule. The path has to meet this rule and that rule, and a walk just needs to be an actual sequence where each vertex goes from one edge, like from one side of the edge to the other side. Okay. So we're going to do the square. Something like W, X, Y, Z. Let's do one of each. So let's do a walk. We'll go W, Z, let's go back to W and over to X. Here, here, back, and over. So that works out. However, I can't call that a path because we've gone over this edge more than once. But if I went Z, Y, X, W, that's a path. So the sequence is okay. Each vertex is connected to the other by an edge. Z to W, W up to X, X over to Y. Sorry, Z to Y, Y to X, X to W. So going like this. Okay, a circuit needs the end to be the same as the start. So we can go, let's go Z, Y, X, W back to Z, and then stop. Okay, start at Z, you end at Z. Each vertex was next to the other one. or connected to the other by an edge. And we didn't reuse any edges. So we had to do like, make sure it was a log, make sure it was a path, make sure the start was the same as the end. Okay, and then examples for the rest of class. So this time we have a graph and a sequence.
Professor, I have a really quick question.
Oh yeah.
Yeah, so I'm wondering in terms of like the circuit in this example, how come we're able to skip W?
Oh, that's my
If that
mistake.
makes sense.
That's me. I skipped it. Z to Y to X.
Okay.
No, I need W. Thank you. Yeah, that's missed.
Okay, no problem. Yeah, I was just wondering if circuit made like an exception. Thank you so much.
No, thank you too. And then back to Z. Yeah. Cool. All right, let's try to make sure this one goes okay. The picture. We'll do this kind of slow and steady. We've got A. B, C, D, E, kind of in a circle. Let's do, there's a triangle between ACD. This. There's also a connection between D and B. Also, there's a edge from D to E. And E goes over to C. That should be it. Looks good. Okay, so first one is DEDCA. Is DT. C. Okay, so got this sequence of vertices. Is it a path? So first you have to check if it's a lock. Are all of the vertices connected to each other by an edge? And then you have to make sure you don't reuse any edges. So go to D, over to E, back to D. So already it's in there. We reuse that edge. So, but let's just see what happens also. DEDCA. Okay, that part's okay. It's this issue where you go from this way, from D to E, and use the edge, and then you go back and use the edge again. So it's not DECDA. DECDA. Okay. Are we ready? Let's do it. Okay, this one is going to C, then to D. Over to A. And it's the same question, is that a path? let's check it out. So we go over to D and then E. Oh, but then this time we go over to C. So this is okay so far. Let's clean this up. Okay, D to E. E to C. This way. Yes. C to D. Okay. D to A. Looks good to me. It was a walk, and we used every edge one time. No repeats. We'll talk about it one more time, but I think that was good. It is a path. So D, E, that's that edge, E to C, C to D, D to A. Okay, so is the following sequence a circuit? We're going to go C, A, D, C. C-A-R-C-U-I-T. Cool. Okay, let's see. C. Goes to A. Then A over to D. It's okay so far. D back to C, and then we're back at where we started. So yes, it is a circuit. Used those edges one time, and it was a walk. Using every edge once makes it a path. And we ended where we started, which is a circuit. One more for this graph. It's A, D, C, D, A. Same question. Okay, A, D, C, D, A, which I cannot see. Okay, starting at A. Go over to D. And then cross to C. Oh no, we're going to go back to D. And then you end at A, so the end is the same as the start, but this needs to be a path as well. So if you reuse that edge, it's not a path, which means it's not a circuit. It was going to go to A to D, and it was the edge DC that you cross over twice. And remember, DC is the same as CD. So that edge was used more than, we used it twice, so we used it more than once. Okay, we're doing pretty good. Wow, there's a lot of examples. So we're probably going to just do paths and circuits this week. Let's try another graph. All right, start with this sort of diamond shape. And then straight down the middle. Another vertex over here. Let's start with some labels. A, B, C. Actually, I'll scoot this up. And E. Okay, we're going to connect A with E and C with E. Okay, so I'm going to go through some sequences and find the strongest definition. So if it's a walk, then we'll say walk. If it's a walk in a path, choose path. If it's a walk in a path and a circuit, then it's a circuit. So whatever definition is the best definition for the sequence. Sequences determine if the following sequences. It's going to be walk, walks, paths, circuits. CIRCUITS. Or none. Or like neither. Cool. First one is going to be A, B, C, D, E. We'll squeeze it in right here. Okay, so it was A to B to C to D to E. Okay, so we're just going to see if the sequence is a block, and then we're going to check out if it's even more than that, if it's a path, and then if you could get circuit, that would be cool, but if it's neither of these, then put neither. So we go, let's get color. A to B. From B to C. C to D. D to E is not good. So this is not a walk, which means it's not a path or a circuit, it's neither. See what I put. I have an answer key. I put none, which kind of makes more sense. Or It's not a walk or path or circuit, so neither works. This looks weird. Okay, we want to see if A, B, C, D, A is a sequence. We want to check out if it's a walk, and then see maybe if it's a path or circuit. Let's do blue. A to B. B to C. C to D. And then D to A. So we have a walk. Every vertex was connected to the other by an edge. We used every edge one time, and the end is the same as the start. So this one is a circuit. Okay. We have CE, and that's it. 1, 2, 3. Let's do C over to E. So each vertex was connected to the other by an edge, which makes it a walk. The edge was used one time, so it's a path. You don't end where you start, so we can't say that it's a circuit, but we're going to go with path. And then like one more. Okay. This is a big one. So we're going to do the whole sequence. Check it out. So A, B, C, A is a start. Then it's D, C, E, A. Again. A, B, C, A, D, C, A, A, B, C, A, D, C, E, A. Okay. Let's find one more color. Start at A. Go over to B. B to C. C to A. A to D, D to C, C to E, and then E to A. So it was a walk. We were able to go from every vertex to the other by an edge. We used all of those edges once, and we end where we start. So this one is a circuit. Okay, so I feel like we have time, and we should probably work on one more. Oh, cool. Okay. One more. The graph starts out as a big square. With a line diagonal. We'll put CFEB. Okay. There's still some more. Right in the middle of BE is another vertex, D. I did the same thing here and put a vertex A. And then connect A with B. And that's everything in the graph. There. Determine if the sequence is a walk, path, circuit, or neither. All right, let me start with FCBAC. Okay. F to C would be here to here, C to B, go across, B to A, and then A to C. So we do have a walk, F, C, B, A, C. You can draw. And it's a path. Every edge was only used one time. Just cross here once, over there one time, down here one time, and across there one time. This one's big. Okay, part 2. A, B, D, E, A. Okay, let's check this. Use blue and go from A to B. B to D. D to E. E to A. Oh, cool. I ended where I started, and I used every edge one time. So first of all, it was a walk, and then using each edge once makes it a path, and starting where you end gets you to circuit. All right, number 3. So it's A, B, C, D, E, F. A, B, C. So we're starting at A, going to B, then to C, okay, over to D. That's not good. Okay, it can't go from C to D. It's not connected to that vertex by an edge. So it's not a walk, and that shuts down everything else. It makes it not a path, it's not a circuit, it's neither. And number 4 will be the last thing we do. It's A, B, C, A, B, C. A. Okay, let's see if we can get it all. A, B, C. A, B, C. And then ending with A again. Let's see how this goes. So oh, sorry, wrong one. We just did this and it was not a walk. This one, A. Over to B. Cool. B to C. C to A. So we've made that little triangle at the top. And now A to B. Let's see, A to A, B, C, A. Well, you start where you end, but you reuse an edge a bunch of times, like A, B, C, and then you reuse edge AB and BC, and you do CB again. So it is a block. And we're going to call it good for today. So we still have more examples for walks, paths, and circuits. And then we're going to hopefully reach Euler paths and Euler circuits this week. Okay, note to self.